Dear all, good day. In today's video, we're going to look into specific algorithms which can be used for parallel processing. Okay, one such is a divide and conquer. I think already you must have learned it in algorithms paper, but this is a slight variation of that. In the sense, we are going to see how merge sort or any divide and conquer technique can be useful in a parallel algorithm environment. So again, we are familiar with the word or with the procedure called sorting. So most common operations that happen in a given computation environment is only sorting. So even if you only have, when you involve some kind of a computation where it doesn't actually involve sorting, but still involves some complex calculations and stuff like that, you can still go about finishing the sorting process and then start with your complicated applications or complicated manipulations, which will in fact bring down your whole lot of complexity. So it also is very, very important in a parallel environment because sorting by itself works in a very, very parallel way. Even when you're going to implement sorting in some kind of a say serial processing also, sorting has by itself some kind of a parallelism involved. So coupling sorting with the parallelism is going to all the more save a lot of time in terms of computation. Now, generally, any sorting algorithm is given by two important efficiency metrics, which we call it as time complexity and space complexity. I'm sure that all of you are definitely aware of these two things. So, what do you mean by time complexity? So, depending on the input, the amount of input that we are giving, the time, how much time maximum it can take to execute an algorithm. This is what you call it as time complexity. Let me read the definition for you. In relation to the amount of the input, time complexity describes how long it takes an algorithm to execute. So there are important three metrics or three notations which you can use to show the time complexity. One is called as the big O notation. Then the other one is called as omega, then the other one is a theta. So now, as you must have already learned, each of these algorithms are represented in terms of their complexity with respect to time in this manner. The second complexity is called as the space complexity. So in space complexity, it is to do with the memory, whereas time is to do with the execution time. The amount of space or the memory which is required to perform the execution of an algorithm is generally what you call as space complexity. So to give you the exact formal definition, so how much memory is actually required to run an algorithm completely? So it includes both the memory which is actually required and also the additional memory which we call it as the auxiliary memory. So the additional memory that the algorithm uses over and above your usual memory is what you call it as the auxiliary memory. So space complexity generally involves both the original memory as well as the auxiliary memory. This we need to remember. Now, let us come to what do you actually mean by sorting in parallel. When we need to actually sort a amount of data in a serial way or in a sequential way, it is okay, but the thing is, it may not be very, very efficient. Hence, if the same process can be done in a parallel way, obviously, we are going to improvise on the efficiency in terms of time complexity, especially. So the output of a sequential sorting in terms of time complexity is defined in the terms of order of n log n. Whereas if you take the same thing, if you're going to implement the same algorithm in a parallel environment, we're going to have only order of log n, because order of n log n is for one processor. You divide it by n. So you will have order of log n, which we can obviously see that the time required to compute complex sorting in a parallel environment is much, much efficient than doing it in a singular or serial way. All right, now we will move on. When we talk about the divide and conquer algorithms, there are two important divide and conquer algorithms which we have. One is called as the quick sort. The other one is called as merge sort. In this video today, we will be looking at only merge sort, where quick sort we will be doing at a later stage. So how does a merge sort actually work? See, irrespective of whether you're going to do merge sort in a parallel environment or in a serial environment, the underlying logic of merge sort is going to be the same. There is not going to be any change in terms of the logic. But how the same process is divided among different processors vary. That is what actually contributes to the much faster pace of completing the execution. Now see, merge sort is one of the popular and efficient sorting algorithms. And as we already saw, it uses an approach called divide and conquer. If you're going to have a very large set of n items, the n would be divided into a number of smaller partitions. And for each of these smaller partitions, the same algorithm will be recursively called in order to sort out the list. Okay, so how does it work? You're going to have an input. You're going to divide the input into two smaller sublists. And sorting of these sublists will then give you two more sublists. And finally, you're going to merge all the sorted ones. So since it is going to use a recursive process, it is comparatively simple to implement and understand. So in general, as I told you earlier, even when you are working on a merge sort in a parallel environment or in a serial environment, the sorting algorithm by itself is very, very powerful and efficient. Let us look at an example for better understanding. Let us say I have an unsorted list called 6, 35, 42, 15, 3, 17, 63, 12, as you see on the screen, which is flashed. Now see, I'm going to divide this into two, roughly, not exactly two, roughly I can divide this into two. I'm going to have 4 elements in one list and another 4 into another list. Now, as you can see in the second thing, I have 6, 35, 42 and 15 in one list, 3, 17, 63 and 12 in another list. Now, these I'm going to call these two as two different sublists. Now, again, I'm breaking down. Since I've already broken down that, I'm going to internally do the sorting within these two separate lists. So 6, 35, 42, 15 will be sorted. So I get 6, 15, 35 and 42. And again, the same thing I do with my second list, which becomes 3, 12, 17, 63. Now, if you look at this particular sublist and this particular sublist, I find that the data within these two lists are already sorted. Now, all that I need to do is when I'm going to merge, I'm going to have an overall merging with unsorted. That is what we're going to do. Okay, now see what happens. I'm going to merge the sorted list and produce the final. So 6 I am taking from here and 15 I am having, but I find that 3 is lesser than 6. So I will start with the 6, then 12, sorry, 6, 3, 6, 12. And then I take 15 from here, then I have 17, then I have 35 from here, then I have 42 from here, and finally I have 63. So I kind of sort in my sublist, and before I can merge these two sublists, I make sure that I am sorting and I am finally merging. Now, let us look into the time complexity. So time complexity of merge sort for average, this is generally, I'm not talking about in a parallel environment. In general, the average in the worst case scenarios, the time complexity is order of n log n. I'm sure you've already learned what is worst case and average case. For better recollection, I would suggest that you go back and see what is average and worst case scenarios. We also have something called as the best case, so you can refresh on all these topics. Okay, so now this even just the order of n log n itself seems to be much efficient, very quick, and that's why many of the applications, they go for time complexity. They go for merge sort as the sorting algorithm. Now, let us look into space complexity. On an average worst case and average scenarios, it is order of n. In case you have a best case scenario, then it is going to be in the order of 1. This is just the overall, irrespective of whether it is the input size. This is the overall time and space complexity in a serial environment. Now, if the serial itself is going to perform to this extent, very well to this extent, imagine how good it is going to be in a parallel environment, which we will be seeing in the next slide. Okay. Now this is just the pseudo code of your merge sort. Whatever we have done so far, the same thing we are explaining here. So first thing, what do we do? If the length is going to be just one, if there is only one element, I'm going to return it. If there is going to be more than one element, then I'm going to divide that into left element, left sublist and right sublist. I'm going to sort and merge in my left. I'm going to sort and merge in my right. And then once I'm going to merge, I've sorted my left list, I've sorted my right list, we are here. And once I'm going to merge it, I'm going to check whether the first element of my left is lesser than first element of my right. Accordingly, I'm going to do the merge. Okay, finally, I get my sorted list. We'll move on to the next slide. Okay, now this is where the topic of our discussion for today comes in. Parallel merge sort. Okay, what do we do in parallel? As we can see, the same process we're going to do, but just with this very, very little difference. Instead of using a single processor, we are going to use multiple processors here. So parallel merge sort is a variation of this merge sort algorithm that takes advantage of parallel computing to sort larger data sets more quickly and efficiently. Imagine I just have one processor which does the sorting, that itself yields me order of n log n. I'm going to have n processors, definitely I'm going to have order of log n kind of a time complexity. So what we are going to do here is the initial list, as usual, I'm going to divide it into sublists. But in general, what happens in a serial environment? Each sublist will be executed by the same processor. But here I'm going to use multiple processors which can do the sorting of all of these sublists. So what happens here? I'm going to complete my task of sorting at a much, much faster pace. And what is very important here? How am I going to concurrently pass all these sublists to different cores is what I have to really look into. So finding the actions that might be performed concurrently is a very key to constructing any kind of a parallel algorithm. All right, let us move on. So this is again the same thing. We are going to take advantage of the parallel processing. The initial list is divided into smaller sublists, which I'm going to sort it and send it to multiple CPUs. So this is going to greatly influence on the time taken, which has to complete my sorting process. Now, let us take this simple example. This example should tell you everything. So I have an unsorted list with, say, 8 elements. So I'm having a processor. Now that processor divides the list into 2, as you can see here. It divides the list into 2, list 1 and list 2, which is given to processor. This is given to processor P0 and this is given to processor P1. P0 again divides the list into 2. Further, so 8 was earlier divided into 4. 4 is now again divided into 2. So this P0 again will have just the two elements. P2 will have 7 and 8. P4 will have 5 and 1. And P6 will have 3 and 6. Again, I'm going to further divide it. I keep on doing that. So at this particular point of time, I find that each processor has only one element in it. Okay, now that all the processes are going to have only one element, I'm going to start merging. Sort, merge, sort, merge. That is what I'm going to do. So P0, what it would do, 4 and 2, it finds that P0 has 4 and P1 has 2. I'm going to sort it. So P0 will now have the sorted list of 2, 4. What will P2 have? It had 7 and 8, which is already in the sorted list. So P2 will be sorted now. Now P4, examining the elements of P4, I have 5 and 1. Again, I find it is not sorted. So I will sort and it becomes 1 and 5. Now again, the next one is 3 and 6. It becomes, anyway, it is already sorted. It becomes 3 and 6. So finally, I am done at this level. So I have got each 4 elements. 8 elements became 4. Now 4 has become, 4 has now become 2. One element has now become 2. 2 has to now become 4. So at P0, I have 2 and 4. P2, I have 7 and 8. I'm going to combine these two. So I will have 2, 4, 7, 8. But fortunately, this is already in the sorted list. Now look at this list of P1, P4, I have 1 and 5. P6 I have 3 and 6. How does it, how do we represent? We have to start sorting it out because it is not in the sorted list. So it becomes 1, 3, 5 and 6. At the final most level, I'm going to combine these two, which becomes 1, 2, 3, 4, 5, 6, 7, 8. So what is the difference here? I'm employing multiple processors to perform the merge sort, thereby making sure that the processing happens at a much faster pace here. Now, I think the other day also we learned about something called as fine-grained parallelism and um, the other one, which is a coarse-grained. Okay, fine-grained means what? The number of task which is allocated is going to be very less. The number of computations inside a task is going to be very less because it is highly fine-grained. So suppose if you have n processors and your data itself is going to be just n, then you can call it as a fine-grained. I'll just give you one simple example here. You need to sort 10 items. Okay, you need to sort 10 items, but you have on hand 12 processors, which means the scenario can have one processor having only one element. This is a typical example of a fine-grained parallel merge sort. Okay, look at this example. I have n. I divide it into n by 2, then n by 4, then n by 8. Finally, I can give even one element having one processor. So to that extent, the thing can be fine-grained. Now, so this figure, I'm just going to read out whatever we saw in the previous diagram here. So this figure shows an example of elements number with 8 elements to be sorted and what would result at each level of the tree. So actually there is no labor actually involved because the n, it's my number of processors small n is going to be greater than my capital N. I have only 10 jobs, but I have 12 processors on hand. So I will definitely have a highly fine-grained parallelism involved here. So each of our 4 processors can operate on separate groups at 2 different items. So finally, when each of these are sorted, I'm going to start merging at a very smaller level. And finally, I will have a final sorted list. This is one case. So here we saw the skeleton. Now we're going to implement values at each level. So I have these numbers. As you can see at the n by 2, the n is 8, n by 2 is 4. I'm having 4 at each level. Then it has become 2. Then it has become 1. Before I can start merging this one and this one, I would sort this one, this one. So this would be 6, 38. This would be 15, 42. This would be 3, 17. And this would be 12, 63. Now again, when I merge these 4, it would become 6, 15, 35, 42 here. And here it would become 3, 12, 17 and 63. Likewise, it goes on and finally I get a final sorted list which is highly sorted and which I have obtained at a much quicker pace. Now this is the pseudocode of your parallel merge sort. I have procedure parallel merge sort. I have ID, the data, n and the new data. So the old data I'm going to sequentially merge the sorted data and it is going to run through from 1 to n, where n refers to the total number of processors you have. You keep on doing this merge and sort and merge, same thing. Finally, you assign the sorted data to your new data and return the new data. So as we already have discussed, the time and space complexity of this is order of log n, and it is going to divide at the pace of order of log n and merge it in the same way. So it is, so in total you have 2 log n or order of log n is the time complexity, and space complexity you have order of n. So we find that there is not much difference in terms of space complexity, but in terms of time complexity there is a significant difference between a parallel merge sort and a serial merge sort. Now, we considered a very hypothetical situation where my number of processors is much greater than the total number of process itself. Now let us consider a very practical example where my n, that small n, that is the total number of processors, is going to be lesser than the actual number of tasks or actual number of data items for which I need to do the sorting. So what we would do is I need to benchmark and check how well my machine is performing. Probably you can imagine the previous one was a best case. Now we will see how it would work in an average and a worst case. Okay, is one where you have fewer processors than the actual component. So in this situation, we are going to divide the work and then make sure the divided work is allocated to the available number of processors. To give you a simple example, I have 8 processes or 8 data items, but I have only 4 processors to complete the task. So I will not be able to divide it to the level of 8 where one processor can be given one data item. I can at the most give 2 or 3 items to one processor. So it cannot be a finely gained one. It will be a coarse one. So on multi-core computers, the OS may inform us when we begin the sort, so we can get that many number of processors. So this is an example. So I have 4,000 items. I divide them into 2,000. See, this is the actual availability of my processors. When I have 4,000 items, I don't have 4,001 processors. I'm having something which is much, much lesser. All right, so I cannot have a very finely grained ones. I have 4,000, then it becomes 2,000, then it becomes 1,000, then finally it becomes 500 plus in each of these. So in this way, we will be able to compute. This is a simple practical example how we can go about implementing your merge sort in a parallel environment. So I have added the link here. If you are for the exam perspective, you may click on this link and have a detailed notes in the link that is given inside the presentation. Thank you all of you. Please prepare a note of whatever we have done.